Hello students, Mr. Courtney here. In this video we're going to be talking about acids and bases again, and we're going to be specifically discussing acidity of a solution. We will define and discuss pH, pOH, we will calculate pH and pOH of solutions. We'll look at how we measure pH of a solution and how we calculate the pH of strong acids and strong bases also. So the pH scale. The P scale is based on a common logarithms, or as some people say, common logs, where if you want to find the P of some number n, you do the minus log of that number. So what is a logarithm? If we're using the base 10, then the log of the number is the exponent to which that number, or which 10 must be raised to get that number. So for example, if we have x is equal to 10 to the exponent of y. So that tells us that 10 must be raised to the exponent of y to give that number, x. That means the log of x is equal to y, because we said the logarithm of a number is the exponent to which 10 must be raised to give that number. So 10 must be raised to the exponent of y to give us x. So the log of x is equal to y. So the pH scale is a convenient way to represent the acidity of a solution. So we use that to tell how acidic a solution is. That is based on the amount of hydrogen ions. Because pH is equal to the negative log of our hydrogen ion concentration. So when we talk of acidity of a solution, we're talking about what amount of protons, what is the concentration of protons in that solution. So we take the negative log of that hydrogen ion concentration, and that will give us our pH. When we look at the pH scale, we'll see several factors. Because it's a log scale, the pH is going to change by 1 for every power of 10 that we have a change in hydrogen ion concentration. And here we see we go from 1 to 10 to the minus 1, or pH increases by 1. Or if we go from negative 10 to the negative 11 to 10 to the negative 10, or pH decreases by 1. So it doesn't matter which direction we go. For the pH will change by 1 for every power of 10 we have a change in the hydrogen ion concentration. As pH decreases, hydrogen ion concentration decreases. Or a better way to put it, as the hydrogen ion concentration increases, pH decreases in this way. And here we see as the pH decreases, we go from neutral, which is at pH of 7, or a hydrogen ion concentration of 10 to the minus 7, down to being an acid. And if we go up to a pH of 14, then it's considered to be a base. Now, in terms of significant figures when we do pH calculation, the number of decimal places in the log number is equal to the number of significant figures from our original number. So if we have a hydrogen ion concentration of 1.0 by 10 to the minus 4, we have 2 significant figures in this number. So if I want to find the pH, it's negative log of my hydrogen ion concentration. Now, since we had 2 significant figures, that means we need 2 decimal places in our log number. So we started off with 2 significant figures here, 1, 2. That means I need 2 decimal places. Again, so the number of decimal places in the log number is equal to the number of significant figures from the original number. Alright, so let's look at some examples. We have to calculate the pH value for each of the following at 25 degrees Celsius. So we're given hydrogen ion concentration, or hydronium ion concentration in the first 2. So we have H3O plus concentration. We only have 1 significant figure, so that means in our answer we should go to 1 decimal place. So to find pH, we take the negative log of 1 by 10 to the minus 5. That gives us 5.0. And we only went to 1 decimal place because we only had 1 significant figure in our original number. Same thing here. One significant digit or one significant figure number in our original number, so we only go to one decimal place. Now, part C is a bit different because we're given hydronium ion, sorry, not hydronium, but hydroxide ion concentration to find the pH. So first of all, we need to calculate our hydrogen ion concentration. Kw divided by hydroxide ion concentration. So we find our hydrogen ion concentration, which is 1 by 10 to the minus 9. And we find a negative log of that number, and that will give us a pH of 9.0. So that tells us that solution is basic because pH is greater than 7. This solution is acidic, pH is less than 7. And this solution is also basic because its pH is greater than 7. POH. Now, POH is similar to pH in the sense that it's the same method used to calculate it. The only difference is in pH we use hydrogen ion concentration. In POH we use the hydroxide ion concentration. So if we have a solution that is 1.0 by 10 to the negative 4 hydrogen, that's a concentration of hydroxide ion. To find the POH, we do the negative log of that number. So we do the negative log of that number, and that gives us a POH of 4.00. And again, just like we did for our significant figures and decimal places, we have two significant figures in our original number, so we must have two decimal places in our log answer. So our POH must go to two decimal places. POH, pH, and Kw. So the relationship between pH, POH, and our ion dissociation constant for water. The product of their concentrations at 25 degrees Celsius for any pure sample of water, we have equal amounts of hydronium ion and equal amounts of hydroxide ion. We said before that this value, the concentration, is 1.0 by 10 to the minus 7. When we find the product of that, we get 1.0 by 10 to the minus 14. We know that is equal to Kw. So what if we take the negative log of both sides? Negative log of hydronium ion concentration times hydroxide ion concentration is equal to the negative log of our Kw. But from our logarithmic, from logs, we know that the log of A times B is equal to the log of A plus B. So your multiplying logs is the same as if you're adding them, but the base must be the same. And so since we're using the same base as base 10, so the log of A times B is the same as we did the log of A plus the log of B. So we can expand this. Now if we find negative log of our hydronium ion concentration, this is the same as pH. This is the same as POH. So we can say pH plus POH is equal to 14. So for any given sample of a solution, the pH plus the POH will always be equal to 14. So that means if I'm given pH, I can calculate POH because I know pH plus POH is equal to 14. So if we want to get the hydrogen ion concentration from pH or hydroxide ion concentration from POH, pH is equal to the negative log of our hydrogen ion concentration. So we take the inverse log or the anti-log. Simple way to do it is to raise 10 to that number. That is our negative pH. So 10 to the negative pH, 10 raised to the exponent of the negative pH, will give us our hydrogen ion concentration. Let's take an example. So if my pH is 7.00, notice I have two decimal places in my log number. So I'm finding the anti-log of this number. So that tells me my answer must have two significant figures or two significant digits. So to find the hydrogen ion concentration, 10 will be raised to the negative 7.00. And that gives us a hydrogen ion concentration of 1.0 by 10 to the negative 7. POH, negative log of the hydroxide ion concentration. So we find the inverse log of POH that will give us the concentration of hydroxide ions. So, similar to how we did with pH to get hydrogen ion concentration, 10 to the negative POH. So we take 10 and raise it to the exponent of the negative POH value. And that will give us the hydroxide ion concentration. If our POH is 3.00 with two significant digits, two decimal places, that means our hydroxide ion concentration must also have two significant digits. So 10 raised to the negative 3.00 gives us 1.0 times 10 to the negative 3. And this here is our hydroxide ion concentration. Now, if we want to do another calculation, here we're given OH. We're given the POH and we want to calculate the hydroxide ion concentration and the hydronium ion concentration. So we're given POH. So the first thing we need to do is calculate our hydroxide ion concentration. So we take 10 and raise it to the negative POH. That gives us 1.0 by 10 to the negative 8. So that's our first answer here. That's our hydroxide ion concentration. Now to find our hydrogen ion concentration or the hydronium ion concentration, we take Kw and divide it by our hydroxide ion concentration. Kw is 1.0 times 10 to the negative 4, and our hydroxide ion concentration is 1.0 times 10 to the negative 8. The bases are the same, so we can subtract our exponents. Negative 14 minus negative 8, 14 plus 8, negative 14, plus 8 is negative 6. So we get 1.0 times 10 to the negative 6. And here again, we started with two decimal places. So that means our answers must have two significant digits, as we've seen here. Now, let's look at the link between these four: hydroxide ion concentration, hydrogen ion concentration, pH, and POH. So if we want to calculate pH, so I want to calculate pH. Given hydrogen ion concentration, we just do negative log of the hydrogen ion concentration. But what if we were given hydroxide ion concentration? There are two ways you can go about doing this. You can go from hydroxide ion concentration to hydrogen ion concentration, then to pH. So how do we go from hydroxide ion concentration to hydrogen ion concentration? We take Kw and divide it by the hydroxide ion concentration. That gives us our hydrogen ion concentration. Once you have your hydrogen ion concentration, then you take the negative log and you get to pH. Or you can do hydroxide ion concentration to POH by taking the negative log of your hydroxide ion concentration. Once you've gotten that, you know there's a relationship between POH and pH. POH plus pH is equal to 14. So if I subtract the POH from 14, that gives you the pH. That will give us pH. So there are two ways you can go about solving this. And if you can know this relationship here, that will help you. If you want to go in the opposite direction, then you just simply do the opposite of what we've done here. Now, in terms of measuring pH, the pH of a solution can be determined using substances called indicators. And these substances are called indicators because they exhibit different characteristics, most specifically different colors in acidic and basic solution. And they're usually weak acids. If they're a weak acid, that means that there's a strong or conjugate base has a stronger attraction for the protons than water. So we're going to have the reaction proceeding to the left, and we're going to have mainly our acidic or acid molecules present. It's not going to dissociate completely in solution. So here we can see phenolphthalein or phenolphthalein at different pHs. At a pH of 7, it's colorless. At a pH of 10, it's pink. Or you see methyl orange at a pH of 2, it's light pink or slightly red. And at a pH of 7, it is orange. So at different pHs, the indicators exhibit different colors. Here we can see our indicator in its colorless in the acidic form, or it's pink in its basic form. And that's just showing us how the structure changes, what it looks like in the different forms when it's colorless or pink. All right, we can also use litmus paper. Litmus paper turns, if you have blue litmus, it turns red in an acid. If you have red litmus, it turns blue in the base. So we use litmus paper to identify substances as being acids or base. Phenolphthalein, we just looked at it. It's colorless in acid, pink in base, and the pH changes at approximately 8 to 10. So the color changes at a pH of approximately 8. Bromothymol blue. It's blue in base, and it's yellow in acid, and it's green when it is neutral. Now the universal indicator is a mixture of several indicators. So as the pH changes, the color will also change, so that it creates what is called a rainbow of colors. Because as the pH progressively changes, so will the color. So you can see multitude of color over a different range of pHs, instead of just seeing 2 or 3 colors as we've seen in the others before. So this is kind of what we're going to see as if we had a combination of all these indicators. As the pH increases, we'll see different changes in color, and that is what is referred to as the rainbow of color. All right, and to continue on measuring pH, the approximate pH of a solution can be measured using indicator paper, or we can measure the pH value electronically using a pH meter. When we use pH indicator or indicator paper, we take a piece of the indicator paper, dip it into the solution, or put it in contact with the solution to be tested. Based on the color of that strip, we can tell what the pH is. So if it looks like this, then we know the pH is 1. If the color is comparable to this, then the pH is 7. Or if it's comparable to here, it could be 10, somewhere slightly 10, 11, depending on the color. So whichever one the color of the strip matches to, that will tell us the pH of the solution. To get it more precisely, a more accurate measurement of the pH, we can use a pH meter. We can use the handheld ones, or we can get more precise and use the electronic ones. And all these will give us these two will give us a more precise or accurate reading of our pH. pH of strong acid solutions. Now, strong acid solutions dissociate completely in solution. So that means if we have hydrochloric acid or HCl gas, hydrogen chloride gas, when it dissociates in water, it produces hydrogen and it produces our chloride ions. So when it dissociates completely. And if it dissociates completely, that means there are none of the acid molecules left. All we have is our ions. So if you're given the concentration of your acid, we have to look, does it completely dissociate? Is it a strong acid? Yes, this is a strong acid. So that means there will be none of this left. Everything will be converted to hydrogen and chloride ions. What is the ratio? Now we have to look at the ratio of hydrogen ions to hydrochloric acid, or hydrogen chloride gas, or Cl with chloride ions to the hydrogen chloride gas. We realize that they're in a 1-to-1 ratio. So if it's 1 molar hydrochloric acid, that means I have 1 mole of hydrochloric acid in 1 liter of solution. So that means if it's in a 1-to-1 ratio, that means I also have 1 mole of hydrogen ions in 1 liter of solution. So my molarity is 1.0 molar hydrogen ions. The molarity of the chloride ions will also be 1.0 molar. So knowing that now, I have my hydrogen ion concentration. I could go ahead now and calculate the pH. Take the negative log of the hydrogen ion concentration. And here we'll see that the pH is 0. So if we had 0.2 molar nitric acid, same thing. Nitric acid is a strong acid. It will completely dissociate. The ratio of hydrogen ions to nitric acid is 1-to-1. So I have 0.2 molar nitric acid. At the end, I would also have 0.2 molar hydrogen ions. Knowing the hydrogen ion concentration, I can go ahead and find the pH. Take the negative log of my hydrogen ion concentration. That gives me negative 0.7. Negative log of 0.20 is giving us a pH of 0.70. So here we asked to calculate the pH of 0.25 molar calcium hydroxide. So this one is different. We're given the base, we're asked to calculate the pH. So if we're given the base, first we need to find the concentration of the ions. It's a strong base. So we have calcium hydroxide. This is what it dissociates to. So we see we have two hydroxide ions. So that means hydroxide ion concentration to the calcium hydroxide is in a 2-to-1 ratio. This is stoichiometric ratio is 2-to-1. That means I have twice as many moles of hydroxide ions as I have of calcium hydroxide. So if my moles of calcium hydroxide is 0.25, then that means the moles of hydroxide ion is 0.50. Now that I know the molarity of my hydroxide ion concentration, I can find my hydrogen ion concentration. So we find POH. So I find POH, and then once I have POH, I know the relationship between pH and POH is that they add to 14. I can subtract that POH value from 14 and I get a value of 13.70. Or I could have used the KW equation, divided KW by the hydroxide ion concentration. Once I get my hydrogen ion concentration, then we could have gone and find the pH. All right, so this takes us to the end of this section on acids and bases, and we've talked about calculating pH. We defined pH and POH. We calculated POH also. We talked about measuring pH of a solution, calculating pH of strong acids, and also, as we did here now, a strong base. So that will take us to the end of this unit and this lesson. Until the next time, I'm out. Blessings.